These are Algebra 2 notes on quadratic regression equations. We are only looking at one example problem today, and it is the one that you see. I'll give you a minute to write it down here. It says that a ball is thrown into the air. Its height is measured at various times and is reported in the chart as given. We are asked several questions about the ball's flight path. The first, we are asked to create a quadratic regression to model the ball's height. So we want to write an equation that relates height with time. Because the ball is not moving at a constant speed, in fact, it goes up and then comes back down. As it's going up, it slows down, and then as it comes down, it starts to speed up. A linear regression equation would not be a good model here. As we'll see, a quadratic regression is a much better fit. Part B, we're asked for the maximum height of the ball. Part C, we want the amount of time it takes the ball to reach the ground. And in part D, we are told that on the way down, the ball eventually will reach a height of 22 meters. We are asked to find the time it takes to reach that height. How long does it take to reach a height of 22 meters? So to create a quadratic regression equation, you're going to need your graphing calculator. Go ahead, get it out, turn it on. And we are going to enter our data into the graphing calculator exactly the same way that we did with a linear regression equation. So we go to Stat, Edit. If you have data in there, you need to clear it out. You can do that by, so if I've got some data in there, I scroll up to list 1, highlight list 1, and push clear enter. You will need to clear list 2 as well. And we are going to list our times under list 1 and the various heights under list 2. So times go under list 1. Scroll over, enter your heights under list 2. Even though it doesn't ask us for a scatter plot, it might be a good idea to take a look at it. You will need to make sure your plot is on. There's two ways to turn your plot on. You can go to y equals and highlight plot 1 and push enter so that it's highlighted, and then it will be on. The other way is by pushing second y equals and manually going to plot 1 and turning it on, making sure it's a scatter plot, relating list 1 to list 2 with whichever mark you want. That last one's kind of hard to see, but pushing graph, I still am not going to see my points. Actually, that's an old equation that I graphed. We can probably get rid of that one. But even still, graph shows me nothing. Usually we start with zoom number 6, which I guess I've got 1 point there, but I still can't see most of the points. To see your points on your graph, you want to go to zoom number 9. Zoom into your statistics. You can just push zoom 9 or scroll all the way down to number 9 and push enter. And looking at that, hopefully we can recognize that a parabola is going to be a much better fit than a line would be. To create the quadratic regression equation, we do it almost exactly the same way that we create a linear regression equation. We go to Stat, scroll over to Calculate, and previously we had been going to number 4, linear regression. Here we want number 5, which is a quadratic regression. My x's are under list 1, my y's are under list 2, We can leave frequency list blank. It is important to store your regression equation under y1. We did that with linear regression equations, but we didn't really do much with it. You are going to need to store your regression equation under y1, and you do that by pushing alpha, trace, and then going to y1. And when I calculate, a couple things are going to happen. The first thing is it's going to tell me my regression equation. That's our answer to part A. That's what we want. So part A, I guess it didn't explicitly ask for it, but part A wanted us to write down the linear regression equation. Our answer there is y equals negative 4.667 x squared. I guess it's height and time, so let's use those variables. Height is negative 4.667 time squared plus 25.730 t plus 17.137. That is our answer in part A. So it gave us the quadratic regression equation. Notice also if I go to y equals, it has typed in not the rounded off answer, but the big long decimals, the entire regression equation under y1. That's what happened when we stored it as y1. And because of that, if I push graph, not only does it show me the scatter plot, but now it puts the curve in there as well. Part B wants to know, based on this model, what is the maximum height of the ball? Sometimes I see students that will put 50.6 because that is the biggest height on the table. Just because it's the biggest height on the table doesn't mean that's the highest point that it reaches. It's certainly possible that in between 2.1 and 3.4, or maybe even after between 3.4 and 4.2, that it gets above 50.6. The directions on here probably could be more clear, but we want our answer to be accurate to the nearest thousandth of a meter, or at least the nearest tenth of a meter. I guess we should go with that since that's what they have over here. So in order to do that, we have graphed the curve. We want to find the maximum point, so we want to calculate the maximum. Second trace, calculate. We want to calculate the maximum. And I need to enter an x value that is to the left and an x value that is to the right of the point I'm looking for. So I'm going to kind of go back to my graph here. Notice this value is probably right around 3, maybe a little less than 3, but it's certainly between 1 and 5, right? So when I go to calculate maximum, I'm going left bound 1, right bound 5. I know for sure that that maximum's in between 1 and 5, and it is the only maximum value in between there. So when it says guess, I can just push enter again. This is my x value, or my time, 2.756, and my height is 52.6. 52.6 meters. Part C, find the amount of time it takes the ball to reach the ground. Notice it's almost at the ground at 6.1, so we should get an answer a little bit more than 6.1 seconds. When the calculator reaches the ground, its height is 0, so we would want height to be 0. So we want 0 to be equal to that regression equation that we graphed previously. So plug in 0 for height. If my height is 0, that means that I want this equation to be equal to 0, which happens right around 6 there. It's kind of hard to tell based on the graph if it's bigger than 6 or less than 6. Based on this, we know it's probably bigger than 6. But I would want to search maybe between 5 and 7. So calculate 0. My left bound is 5, and when I push right bound 7, it gives me an error. Error invalid. Invalid means that when I typed in a right bound of 7, that 7 was not on my graph. Notice write down 7. That's where it's spitting out the error. So you can go to on that error, and it's going to show you where you made your mistake. You can change it here. So 7's kind of off the graph. I can either change the window so it includes 7, or maybe try 6.5 or 6.2, or start shrinking it down that way. Let's go ahead and change the window. Let's do it that way. Notice my window only goes out to 6.71. If I make my window go out to 8, now I can successfully search between 5 and 7, no problem. Calculate my 0. It is between 5 and 7. 6.114. And part D says on its way down, the ball reaches a height of 22 meters. Find the time it takes to reach this height. So we want our height to be 22. 22 equals negative 4.667 t squared plus 25.730 t plus 17.137. We're going to add a part E to this as well. Sorry. Remember, when we're solving, we want our equation equal to 0. So I want to subtract 22 from both sides. So I've got this regression equation. Instead of subtracting 22 from this, that's part of my regression equation. I'm just going to subtract minus 22. And this guy right here is all that regression equation that I have typed in. So we've got a couple options on how we can take care of this on the graphing calculator. When we go to y equals, we could scroll all the way to the end and type in minus 22 at the end of this, and eventually you'll get there. It's not the most efficient method, but you can get all the way to the end and type minus 22. Graph that and calculate the zeros. That would work. A better option is to scroll down to y2. We want to take this equation that is in y1 and we want to subtract 22 from it. So the same way we stored our regression equation as y1, alpha trace, we can do y1, that's the equation that is in y1, minus 22. Now the problem is, if I graph right now, it graphs both curves, and I don't necessarily want both curves. And if I try to calculate zeros, it's going to calculate zeros on my first graph that is shown, y1. I don't want to clear out my regression equation, because now y1's going to be gone. So when I try to graph y2, I'm going to be doing 0, no graph, minus 22. To turn the graph off, notice the equal sign is highlighted. I want to push enter on the equal sign so that that graph, I missed my equal sign, or my enter sign, enter on the equal sign, so that that is no longer activated. So notice now I haven't cleared it out. It's still stored in there, but it's not going to graph it. The only one it's going to graph is y1 minus 22, which is what I want. Notice it doesn't go through the points. That's okay. I shifted it down by 22 units. I want to know, when is the equation 0? It looks like it's 0 right around here. But more importantly, it's 0 over here, because remember, it's asking on its way down, it reaches a height of 22 meters. So yes, it does pass through 22 meters here somewhere, but it's still on the way up. The height is still increasing at that point. So we want to calculate that 0 over there. It is between, it's hard to tell, push graph, 1, 2, 3, 4, it's between 5 and 6. Calculate the 0, it's between 5 and 6. And we get 5.317. .317 seconds. So 22 meters. Notice 22 meters is going to be in between here. Whoops. But closer to this one. That makes sense. Seems reasonable. I mentioned before that because these aren't accurate to 3 decimals, these necessarily wouldn't be. I'd make sure that you know how to find it accurate to 3 decimal points. Don't round these numbers off and then plug in a time. It is very possible that the heights would be rounded to 3 decimals, and now your answer, it would appropriately be 3 decimals. Part E, last part. Part E says use the model to approximate the height at 4.7 seconds. And again, let's be accurate to 3 decimal points. Maybe approximate's not the best word there. So we want to plug in 4.7 for time. And again, if I want my answer to be accurate to 3 decimals, I don't want to plug 4.7 in right here because these numbers are rounded off. So if I have rounded off numbers and I get an answer and then round that off, odds are good that it's not going to be accurate to 3 decimal places. So we have better options on how to find a y value given an x value, because that's what we're trying to do, right? We're given an x, a time, and we're looking for a height. Let's go back. Remember, I want my height now, and my height is not y2. It was y1. So let's go back. We don't need this anymore. Let's turn our y1 graph back on. There are 2 different ways you can find this. If I look at my table, which is second graph, notice it gives me any y value for x equals -3, -2, -1, and so on. The problem is it doesn't give me when x is 4.7 on the graph. But I can take care of that by going to table set, second window, and it asks me, where do you want to start your table and how much do you want to change it by? So right now my table starts at 0 and goes up by 1. If I started by 0 and go up by 1/2, now my table is 0, 1/2, 1, 1.5, 2, 2.5, and so on. Going back to table set, second window, I'm just going to start my table at 4.7 because that's the one I want. Right? Yep, 4.7. Second graph, we'll pull up my table. At x equals 4.7, notice my y is 34.969 meters. If it only gives you 2, like here it only gives you 2, but you need more than that, you can, scroll down to where you want it, highlight that, and notice down here it gives you the big long decimal. Another option on finding a y value for a specific x is go to second calculate, second trace, the pull-up calculate, go to number 1, which is value. It wants to know what x value do we want. We wanted 4.7, and it'll give us the y value, 34.969. Same answer we got this way. That's it for today's notes.